Welcome to class number 23. In this class, we will discuss a topic called TTL, which is a field at like layer 3 in the IP packets. So TTL stands for time to live, and we will see how when a route loop occurs, what happens to the packets. So this is the topology we use for this lab. So we have PC1 and PC2, and there are 4 routers in between. So PC1 has the IP of 10.0.0.1 and PC2 has the IP of 192.168.0.1. So we have 4 routers in between and we have configured all the routing. So when PC1 tries to send a ping request, so it will put the destination MAC address 192.168.0.1 and it will send it to R1. So once the packet arrives on the R1 checks its routing table for the destination IP. So if you go back and see R1's routing table, 192.168.0.0/24 via Ethernet 1, and the next hop is 12.12.2, which means the connection between R1 and R2. So then R1 routing table says send the packet towards R2. Then the packet will arrive on R2. Once it arrives on R2, R2 will again checks its routing table to see where it should forward the packet destined to 192.168.0.1. So then it will go ahead and check its routing table, and this time the next hop is 23.23.2, so which is towards R3. So that's correct as per this topology. Once the packet comes to the R3, again R3 will check routing table and see to send packet to 192.168.0.0, it needs to send it to 34.34.2. So that is towards R4, and as per the topology, routing so far good, and 192.168 is directly connected route to the R4, and we can see that in the routing table as a connected route. So it should be good. So the ping request from PC1 to PC2 arrives, and PC2 will reply back with a ping reply, and the destination this time is the 10.0.0.1. And if you check the routing table, the packet travels all the way to PC1 based on the routing table. So everything looks good and working fine as expected, no issues here. So let's see this topology. So this is also like same topology, but I did some routing changes. So let's see for the same ping request what will happen. Okay, so now the same PC1 is sending a packet to PC2, and the packet destination IP is 192.168.0.1. so this packet comes to the R1. Once R1 receives this packet, what it will do, it will check its routing table 192.168.0.1. so this is the route matching for that packet, and the next hop is 12.12.2, and it's through Ethernet 1. So as per this topology, this is the correct route. So packet will go this way. Once it arrives on R2, and R2 routing table states to send any packets to 192.168.0.0/24, the next hop is 23.23.2 via Ethernet 2. So this is also fine, the packet goes here. Let's check on R3 routing table. To send a packet to 192.168.0.0/24 network, it needs to send it to 23.23.1 via Ethernet 2. So 23.23.1 is actual R2. So it will try to send the packet here. See, this is where I made a change to the routing table on the R3. The actual route should be pointing towards the R4 34.34.2, but I intentionally made this wrong routing change. Okay, so now the packet goes to the R2. What R2 will do? R2 will again check its routing table and see, and the routing table says send it this way, so it will send it here. The packet comes on R3, and what R3 will do based on the routing table, it will send it towards R2. So as you can see, this process goes on. So if there is any routing table misconfiguration in the topology, the packets may get into the loop. So in this example, we only have one ping request, but in real-time production network, you might have like thousands of devices between behind the R1, and you might have like thousands of devices behind R4. So each system can generate like hundreds of packets. If there is any routing loop like this for those networks, then all the packets will be circulated on this loop between R2 and R3. So each link will have certain bandwidth. So what happens after some time with these route loops, all the links will be saturated with this circulating packets. So they will never die, right, in this case. So this is where the TTL, time to live, helps. So TTL is a 8-bit value. So that means it can be 0 to 255, the maximum value. Okay. So in this topology, if you try to ping, you can see you will receive ICMP type 11 message back. So PC1 is trying to ping 192.168.0.1. As there is a loop here, what will happen after some time? The TTL value will get expired. So how it get expired? So whenever a IP packet is sent out from a machine, the machine will set a value between 0 to 255. So some devices set it to 255, some devices set it to 164, some devices set it to 128. It depends on the operating system. So it does not matter what value it has been set. So what happens is, for suppose this PC1 initial value it's set on the packet when it is sending out, let's say it's 64. So whenever this packet crosses any layer 3 device, means it could be a router, firewall, or load balancer, anything that is performing routing, what will it will do is it will perform some operation on this field. So it will subtract 1 from the actual TTL value in the packet. So the packet TTL value here, if you check, it should be 63. Here it should be 62, 61. Okay. So again this R3 will send packet to here, right? So it will come to here. Again it will subscribe to 60. Then R2 will send it to R3 in this loop topology. So it will become 59. Then it will send it to here, 58. So this way, after some packet going loop around, the value will become 1. So whenever a device receives a packet with 1, if it tries to retract, the value will become 0, right? So in that case, the router understands this, okay, this packet is going in the loop and it reached the value close to 0. So it sends a TTL expired message. So in this case, if you see, PC1 sent a packet to 192.168.0.1, but it never reached PC2 because there is a loop occurring here. And after some time, this packet is being in the loop. If you see 23.23.1, so whenever it comes here, the TTL value became 1 and it cannot subtract with -1 because the value becomes 0. So then it identifies that packet as being in the loop and the TTL is expired at this stage. So it will just send that ICMP 11 message back to the client stating that, okay, I have received a packet, but that is TTL, the packet TTL is getting expired. Okay, so that PC1 will know that, okay, so whatever the machine I'm trying to reach, it's something occurred in the network and it never reached the PC2, and one of the devices in the path mentioned that the TTL value is being expired. Okay, so the ping is not successful in this scenario because the packet will never reach PC2. So this TTL value will be at the IP header information along with the IP header. Okay, so this is not applicable for the frames. Frames means which only have the like a destination MAC address and the source MAC address. Okay, so we are only talking about the packets of IP. So whenever we try to ping, you can also see an option to mention how much TTL if you want to set manually, -t in this example. So the default is 64, but if you want to increase the TTL value of the packet that you are testing, you can do it by -t option. Okay, so this is the trace route. We are, if you can observe, so PC1, from PC1 we are doing a trace route. If you can see, it went to 10.0.0.254. Okay, that's good. And next it went to 12.12.2. That's good, it went here. Then it should go to 23.23.2. Yes, it went there. Then in the correct topology it should go to 34.34.2, but you can see it is going back to 23.23.1. And next it's going to 23.23.2 this way, and next this way. So if you see any issues like TTL expiring message or anything, if you do the trace, if you see the packets are looping between two devices, you can simply observe this by doing a trace route or ping. Okay, so trace also has the option to specify the TTL value. Okay, so in this case it is just using 8. What happens means, after 8 packets, after packet going around in the loop for like 7 times, then it will get the TTL expired message. So this is a Wireshark example to see where we can see the TTL field. So from this PC 192.168.1.1 trying to ping 8.8.8. So if we click on this packet, you can see in the layer 3 IP protocol layer, you can see the time to leave is 64. So it is the initial value that has been set on this machine. Okay, because I'm capturing on the client side. So, and this is the capture on the client side, and this is the response from the server. So it means this packet not been initiated on this machine. So this is the ping response we got. Okay, so if you look at the TTL value is 60. So in this case I can assume that maybe the destination like 8.8 has some set default value of 64 or something, then it crossed like some 4 routers, and then the TTL value becomes 60. Okay, so TTL value also on the packets will help us to understand how many hops the packet has been crossed. Okay, layer 3 devices, not switches. Switches will not look into the like layer 3 information, so switches only will look into the Ethernet part only. Okay, right? So any layer 3 device performing routing will subscribe the TTL value, and whenever the TTL value becomes like close to 0, like 1, then the device will send ICMP 11 message back to the client, whoever initiated that connection. So for this class, assignment will be like build similar topology and create a loop, and then perform the ping and perform the trace to identify the loop is occurring as per your configuration. Okay, and also try to capture the packets on your PC and identify the TTL values for the sent packet and the return packet, received packet. So when you try to configure the dynamic routing protocols, it is you should be very careful, so that like if you do any like small type of misconfiguration, it will generate route loops. Okay, so you can do some research on how OSPF, BGP, and when you do the redistributions between them, how the route loop can occur, so you can avoid them. Okay, so in this lab we are only like doing static configuration, right, to reproduce the loop scenario, but in real time most of the route loops occurring only because of the like dynamic routing protocols. Yeah, so that's it for today's class. Thank you. Bye.